Hello, everybody. Thank you for the kind introduction. I have to say it's at the same time exciting and a bit sad that I'm giving this talk for a Czech center in New York while I'm sitting here in our apartment in this cozy corner, and we are going to leave this apartment quite soon, in about a week. And I have to say it was really exciting 10 months, especially the end was kind of adventure. I mean, for everybody, but you know, many events like this move to online space, and I think it gives like additional value in a sense that like people all around the world or states can join. I will start screen sharing. Also, I wanted to thank once again to Fulbright Committee and Czech Technical University for supporting me in this stay. And now let's start screen sharing. So now you should see the presentation, hopefully. Also, like a technical recommendation, you can, if you are using computer, you can switch to so-called side-by-side view somewhere on the top of your screen. You can pick this option, and then you would see both me and the presentation. So I will talk about my research I started at the Czech Technical University together with my colleagues. It's called distributed manipulation, but because I wanted to find some more attractive term for that, I came up with this title for this presentation, Contactless Choreography. And you will see why, because we are, in a sense, able to manipulate many objects at once and almost let them dance, as you can see. The structure of my talk will be roughly that in the beginning I will try to show you what's currently available in this field. Then I will tell you about our contribution, and I will end with some fun projects. So let's go into that. If I talk about distributed manipulation, I'm not sure if you can imagine something. So look at this picture. This picture somehow shows standard manipulation. Somebody is taking somebody else in their hands. So from technical point of view, the actuators, in this case hands, are localized somewhere. In distributed manipulation, on the other hand, active elements, we call them actuators, are distributed in space. So that would look like this. So this is distributed manipulation. You can, it's called crowd surfing or stage diving. In this case, active elements or the hands are distributed in space. You have many more actuators than you need. We call it that the system is over-actuated because you have like many more active elements that you need. So in a way, you can say, but that's not efficient. Well, it's partially true, but it brings some advantages. For example, you can manipulate not only one person, but many at the same time. And also, if some part fails of the let's call them manipulator, it's still working. So now let's go to more like a technical world. this is an example of distributed manipulation in industry. It's called celluveyor. It's basically an array of many wheels that are controlled individually. And as I mentioned before, you can manipulate not only one object at a time, but many objects. And it's really nice because you can easily reconfigure the motion because you have many wheels controlled individually. So as you can see here, you can design like a trajectory for each parcel in this case. But you can find applications of distributed manipulation not only in industry. This is a platform from MIT MediaLab, from group Tangible Media. And it's an array of rods, as you can see, that are controlled individually. And thanks to this, you have like an active surface. So it's a very nice artistic object, of course, but their idea goes even farther. They are trying to create like a physical manifestation of some information inside computer. They are trying to create like so-called radical atoms, physical manifestation of bits inside a computer, so that you can really touch the information or interact with the information. But for me, even more interesting field or even more interesting application of distributed manipulation is in micro world. So let's go into, or let's dive deep into micro world. So this is standard ruler. If we zoom in to like first three lines, it would look like this. So those blue bars are now separated by 1 millimeter. If I put my hair there, it would look like this. This is not on my hair. Then on the right side, or to the right side, we can put red blood cells. So let's put red blood cells there. They are hardly visible because they have like 6 to 8 microns, 6 to 8 micrometers. So I will put there something bigger. Those are polystyrene microparticles with 50 microns in diameter, and we use them a lot in experiments. You will see them later. So that's why I'm showing them here, just to get an idea of the scale. Now, what's challenging in the micro world? Let's say you want to manipulate those red blood cells or those beads. Now, why it's difficult? The reason can be explained here. This is a clip from a movie, Fantastic Voyage. It's an old movie. It's about some team that inside like submarine that was miniaturized or like a shrink down, and then injected to body of, by coincidence, some Czech scientist to perform like a microsurgery there inside the body. But if you see the movie, you can see that the people there on like in a micro world behave really similarly to what we are used to from our macro world. But that's not what would happen in our that's what, well, simply the physics doesn't work like that. For example, what would happen? They would be cold, probably really, really cold, because the generation of heat is proportional to volume of our body, while the dissipation of heat, like how much we are losing the heat, is proportional to surface of our body. Another problem is with seeing, because their pupils would be really close to or even smaller than wavelength of the light. So problems like this. So the problem is with scaling of forces, because let's say we have some microparticles here, or just spheres with a radius r. Now, if surface is proportional to r squared, the volume is proportional to r to 3. So if you scale something down 10 times, surface goes down 100 times, and volume goes down 1,000 times. So the ratio between the surface and volume goes down again 10 times, because the ratio is proportional to r. So if you have forces like let's say gravity is so-called volumetric force, because it's proportional to volume. And then if you compare gravity to some surface force like adhesive force, it can happen that at microscale, those surface forces would be or prevail the volumetric forces. So common problem at microscale is that if you grip, if you have like a gripper and if you grip the object, it's quite problem to release it, because it will get stuck to the gripper. So this calls for like a special tools if you want to manipulate like small objects, micro objects, cells, things like, or small droplets. Also, the illustration of why the micro world is different is here. This is water measurer, I hope. and it can walk on water, but we cannot. And the reason is here in scaling of forces, because it uses like a surface tension, and it's enough to support like the gravity or the gravitational force. So now, what are those special tools that you can use at microscale? Those are micro robots. Maybe just give me a second. I'm sorry, just quick interruption. So those are microscopic robots. They have legs, and those legs use piezoelectric crystals to like vibrate, and thanks to that, those robots can move around. And also they have like tiny tools, as some probes here, or this guy has a micropipette, so it can, if we zoom in, you can see that using this micropipette, you can then take some cell, move it somewhere, things like that. And it would be really hard to do this using, I don't know, a tweezer in your hand. And then there are like another ways how to do micro manipulation. So the previous one was kind of standard. It was like a small robot. But in this case, you can use laser to manipulate the objects. You may think that if you shine a laser on some object, the object would be moved away, like from the laser spot. But if the object is translucent, it will be centered, so like attracted towards the center of the beam, and it allows you to manipulate the objects by like changing the location of the laser spot. And you can see it here. So in fact, here you can see not only one laser spot, but several spots. And the trick is that, well, You may know like laser scanners from concerts, drawing like some pictures, you know, or patterns. And the trick is that there is only one laser with some so-called galvo system of mirrors that deflect this laser beam. And then by turning the laser beam on and off, you can create like several laser spots, as you can see here. Just to give you idea about the scale, those particles have like 1 micron in diameter, and you can let them almost dance, as you can see. But it has like a serious application as well, because it can be used for manipulation with, I don't know, DNA or some spheres with some activated surface that can then interact with some biological things, for example. Another way how to use light for micromanipulation is shown here. This is from University of California at Berkeley. And the principle is different here. There is almost like a standard projector that projects pattern on a special layer, and this layer can change conductivity based on if it's illuminated or not. So if you illuminate this layer, it will get conductive. So you would create like a virtual electrode, and then because of interaction between the electric field and the objects, you can then manipulate them. Then we are still in a world of using electric field to manipulation. So in this case, we have array of electrodes, again, array of physical electrodes, individually controllable. And if you activate the electrode, you can change a so-called or contact angle between the droplet and the surface. And it means that you can turn the surface to be either hydrophobic or hydrophilic. And thanks to this, you can then manipulate the droplets, as you can see here. It's very, very, very cool. And the reason why it's important, not only it's like nice visually, the reason is that it can be used for so-called lab on chips. So, and the idea is that if you have a process in standard lab doing some chemical experiments or biological experiments, you can scale it down, miniaturize it, which makes it faster and cheaper, because you need like smaller amounts of liquid. You can do experiments in like a fraction of what you need in standard experiment. And also it can be much faster because you can have many manipulators like this. So it can be parallelized. You can do many experiments at once. So that's why it's important. This is the principle basically shown here. So again, droplets are manipulated here. Those are like micro tubes that allow to like inject fluid and then move it away. Then this device can do, I don't know, mixing of droplets, stuff like that. So standard processes that you would do in the standard lab, but at micro scale. This is another platform from Silicon Biosystems. And in this case, you can see some cells here tracked by computer. And what you cannot see is an array of electrodes. You can see it here now. So again, there is like a large array of electrodes, and by turning them on and off, basically, it's just roughly said, you can induce the motion of particles. And then you can perform like analysis. You can analyze them, and then based on the results from those analysis, you can filter them. You can move them out of this machine and analyze them somewhere else. And when I mentioned electric fields, you can use magnetic field for manipulation as well. So in this case, around this circle, it's in fact phantom eye. So around this eye, there is a bunch of coils, and those coils are used to create and shape magnetic field. And then if you look closely here, you will see like a tiny magnetic object that can move within the eye. And then the system, it was developed at ETH in Zurich. It's called OctoMag. The idea is that the small object within the eye can be used for microsurgery or delivery of some drugs. Well, by the way, it's a really interesting motivation to use magnetic field to drug delivery inside your body, because you can really target the place you want, so it would decrease the toxicity of the treatment. And this is last method that I wanted to mention that can be used for non-contact manipulation, and it uses ultrasound, because it's a work from University of Bristol, and here you can see array of transducers, let's simply said speakers, and each speaker plays one node. Well, they all play the same node, but what's really like important, that they use different phase shift or different delay, and thanks to that, you can use like interference between those waves, and like create place with low pressure or high pressure, and create like a trap. So you can see it here. Those colors represent the phase shift or the delay, and then the particle is trapped in like a low pressure, and then there is a high pressure around, or there is like a silence here, and then it's really loud everywhere else. And then the clever computer system can change the phases or change the delays of all those speakers, so that you can move those places of silence and really loud music. So you can create almost like a tractor beam. So this was about tools and approaches that are already available. And now I would like to tell you a little bit about what we are working on with my colleagues in Prague. And also, I wanted to mention that if you want to ask some question, you are encouraged to do so. And for that, you can use a chat. So you should be able to open chat somewhere on the bottom of your window or somewhere, and you can write a question if you want, and I will be happy to answer it probably after I finish. So go ahead. So now let's go to Prague. What we are doing, what we are working on. So because I'm from Department of Control Engineering, we focused on mathematical modeling of systems, and also we focused on design of control systems. This is like just virtual example of distributed manipulation in 1D. So here we have like set of actuators that deform this surface, and now controller is giving a task to bring those objects to final destination, and the final destination is obviously represented by those lines. So the control system has to know like the behavior of the physics, has to be able to model, or it uses mathematical model to somehow derive what's the suitable activation of those actuators. So we are solving like this problem in general, but then also we are building different or various physical platforms. So for example, this one is similar what you've already seen. It uses ultrasound for manipulation, but it, in comparison what other people or other researchers do, we don't do levitation of objects, even though we can do that, but we wanted to do something different. So we tried, especially my colleague Josef Matouš, tried to do manipulation with objects on surface of some liquid, in this case water, and then you can generate like again some place with a high pressure, and using this point of high pressure you can push things around and almost let them dance. Then we do manipulation using dielectrophoresis. So, and I think you know dielectrophoresis, and I will try something a bit risky. I will try to do a live demo or experiment. So I will stop sharing. And so maybe you try this experiment. So you can use either comb, or I have this party balloon here, and I have like a bunch of paper pieces here. So now if you charge the balloon or the comb, I will try to do that, we should be able to see interaction between the electric field induced by the balloon and paper pieces. And it works only if you are dry, which I'm not. Oh, well, I can see something. I'm not sure if you saw it. So maybe once more. Oh, yeah, perfect. So what's happening here? It's dielectrophoresis. And I will turn on screen share again. So it's dielectrophoresis, and dielectrophoresis allows you to manipulate uncharged objects using electric field, because those paper pieces were not charged, because otherwise they would interact between each other. The principle is that the field of the balloon will create like an induced electric field within those paper pieces, and this induced field then interact with the field of the balloon. So this is how it works. This is how our experimental setup looks like. We have some electronics around, and this is the important part. It's a microelectrode array. And there is a microscope, of course, because otherwise we wouldn't be able to see it. So now what you can see under the microscope. So this is electrode array, and you can control each electrode individually. And here you can see microparticle. In this case, it has like 100 microns in diameter. By the way, this was from some microrobotic competition, and the task was to steer the objects through those gates. And when I mentioned control system, I have to mention also that what's really important for the control system. Control system has to be able to see what's happening in the real world. Obviously, we are using like microscopes to do that, to observe what's happening and measure like a position of the objects. This is a sensor that we've developed that is able to measure not only position in 2D, in 2 dimensions, but in 3D. So it's really useful. But what's a little bit tricky here is that this is, by the way, this is an image that is captured by standard camera without any lens underneath a glass slide with something. And I'm not sure if you like this picture or if you are able to see what's there. I'm not, to be honest. The reason why it's kind of ugly is that because at micro scale, we are getting closer to wavelength of the light. And then those circles are so-called interference fringes. So it's there because of physics. But really nice thing is that you can, if you are able to describe propagation of light, you can do so-called backpropagation and reconstruct the image. So this is, it's on the right side. So this is an image that is captured by the camera. On the right side is image that is then like computationally backpropagated. So you can now clearly see that there is some microparticle, and this is probably like a dust particle. This is our system that uses dielectrophoresis for manipulation. It's a top view from a microscope. Here you can see electrodes individually controllable. And here there is 50 microns polystyrene bead or microsphere. And this circle represents like a desired trajectory. So the control system, this is nice visualization of what's happening there. The control system tries to generate and shape the electric field in a way that the objects move as you want. And it's really important for some applications. For example, you can use this for manipulation with cells. You can then bring cells together, see what's happening, how they interact, and then based on this interaction, you can separate them and filter them, for example, or categorize them. This is another video of the similar setup, just without those colors. The colors, by the way, represented the phase shift again of the electric field. And then we do manipulation using magnetic field. We are trying to develop magnetic manipulator. So it should look like this in the end, but so far it looks like this. It's an array of electromagnets, and electromagnets in this case are used to create and shape the magnetic field. And we have to develop mathematical model that is precise enough and also fast enough to be evaluated in real time in like a fraction of the second, because the mathematical model is used by the control system to find suitable currents for each coil, so that the objects move as you want. You can see it now in how it works. You can see it here. So you can set the desired position by touching the iPad here, and now see the object moving here. And again, really important advantage of distributed manipulation is that it allows parallel manipulation with many objects at once. So here we are able to manipulate like 3 of them, change trajectories, set positions. So again, possible application is in industry, for example, for like intelligent conveyors. This is an example with 6 objects, and the balls are changing formation from triangle to circle. So now it's triangle, now it's circle, triangle, circle. And of course, you can think about other applications as well. For example, you can use it for assembly. So instead of like picking individual parts and assembling them together, you could do this parallel assembly. So they can move at the same time. And it's much nicer, but also more efficient. And also, yeah, you can easily reconfigure the system. It can be used for like different final products. And we are able to manipulate not only solid things, we can manipulate liquids as well. And the driving force here, or the underlying phenomenon, is magnetohydrodynamics. So it's an interaction between current flowing through the liquid here and the magnetic field. And then by changing the magnetic field, you can change the flow. You can like shape the flow, which is really nice. And not only nice, even though I really like how it, well, I really like those patterns. It has some practical application as well. For example, like you can enhance mixing of some liquids that don't mix otherwise. Because some liquids, you know, are hard to mix, especially at micro scale. And this brings me to the last part of the presentation. I wanted to show you this, that you can use magnetic field to manipulate so-called ferrofluid. It's like a mixture of some oil and tiny magnetic particles. So this ferrofluid then reacts to magnetic field that and you can do for example, magnetic snake driving around, or some people created clocks, for example. So it's really cool. And I have to say that I really like this mixture of engineering and art, or visually appealing things. So at the end, I would like to show you some like side projects that I'm working on. So over the time, I developed strange passion in decorating eggs. Yeah, using this robot. It's called Eggbot, and I'm using math, in this case some equations, to design the patterns, or to generate the pattern. So then you can change like some parameter, and it would cause the pattern to change. It's like it's so-called generative design. And once I started with this, I realized that I can go further, and I can use so-called stroboscopic effect to animate those patterns. You will see it here. So what's happening here? This is not computer graphics. But it's like optical illusion that you may know from movies. If you look at like wheels in a movie, it appears like, or it seems like they are turning in one direction or in another direction, and the reason is, or the cause is, the stroboscopic effect. So I'm using the stroboscopic effect here to animate those patterns. So this is from next year or another year. So in this case, I used a special paint that changes color if it's illuminated by laser. This device on the right side is scavenged from laser printer, and I'm able to like change the pattern on the egg using the laser. It will like be remembered for a while, and then when it's rotated, you can do animation, or it will seem to you that it's animated. And I'm doing not only Easter eggs, I'm decorating also Christmas ornaments. So again, this is similar principle used here for animation or almost dancing of the patterns. So that's why I decided to show you this within this talk about contactless choreography. So that's all from me. Thank you for watching. If you want to contact me, you can reach me by email. But before you go, I'd like to encourage you once again, if you have some questions, please write them into the chat that is available somewhere in the bottom of the screen, and I will be happy to answer those questions. So let me check what's there in the chat. So now I see, I hope, where you be, could you see the slides? Because now I read the message from Patricia that she wasn't able to see the slides, so I hope it wasn't the case for everybody. So thank you very much for tuning in. I will wait just a couple of seconds. If there is some questions, thank you all. And because I don't see any question, I will probably thank for this opportunity to Czech Center in New York for inviting me. And I will give the stage back. So bye, guys.
All right, thank you so much. That was so very interesting. Maybe one more last question. Can this technique be used, an example, for targeting tumors? Let's say these particles will be able to penetrate particular place in the body.
So those techniques can be used for like some treatment of cancer, but usually like outside of body. They can be used for some, let's say, filtering of I don't know, white blood cells that can then somehow interact with the cancer, for example. But if you want to manipulate things inside your body, it would be difficult to use electric field, to be honest, because you would need really strong electric field for that, and it wouldn't be you wouldn't like it probably. But but you can use magnetic field. That's so as I mentioned, it can be used for like targeting of drugs inside your body.
Oh, that's exciting and certainly very useful. I guess like in casinos, they could use it as well, right? To spot the ball at the right place and so on. At least that's how I always imagined it works.
Oh yeah, I was thinking about using that Magman platform for creating like a magic table. So
yeah, and you can play
doing like a magic performance.
Yeah, that's great. So interesting. So thank you so much. Our time is up, but I definitely hope we can continue talking with you one day at the Czech Center in New York, and to learn about more revelation as this discipline evolves. So, and thank you all again for joining us tonight, and please join us for our future programs here at the Czech Center New York online. So stay safe and see you very soon.